We'll be going over this problem, and if you haven't already, go ahead and read the problem, pause the video. But if you already know the problem, here's a quick recap. So we have this charged rod of a total charge Q, and this rod exhibits a electric field at this point right here, which is at x is equal to 50 meters. This rod is 25 meters long from x is equal to 0 to x is equal to 25. This is equal to L. And of course, again, the total charge of the rod is Q. So whenever we need to find the magnitude of electric field, we typically rely on the equation that E is equal to K Q over R squared, where K is a constant, Q is the charge, and R is the distance between your 2 points. But this is for point charges only. And in our case, we actually have an entire rod, which obviously isn't a point charge. So we can't really rely on this equation straight up. But we can utilize this equation to figure out how much just a small portion of this rod produces a electric field onto the point and add up all the small portions of the rod. And the way we do that is that we find a dE, or a small portion of the total electric field, and dE is equal to K dQ over R squared. And while I'm at it, I should change this Q. We'll rewrite these equations to fit what we're given. This is K times Q over R squared, K times dQ over R squared. Now we're given something that we can actually work with. So we're going to be looking at a small section of our rod, and we're going to look at the small charge that small section of the rod has, and we'll be able to calculate just the electric field from that small section of the rod. So it looks like we have everything except dQ and R. So since Q is equal to lambda over L, a small section of the charge, or a dQ of the charge, is just going to be lambda times our small section of the rod, which is dx. Pretty simple. And now R is the distance between your test point and your field point if you're using this equation. But in this case, it's gonna R is gonna be the distance between this point and our field point here, and this will be R. So we can say that in this direction, from the origin to our dx is called x. Therefore, from our dx to 50, it's going to be 50 minus x. So this will become our r. So here we have that r is equal to 50 minus x. Now we can substitute everything in to get dE is equal to k lambda dx all over 50 minus x squared. Now, to get rid of the dE on this side, we're going to have to take an integral to give us just e, meaning that we have to take an integral on this side. And we're going to be integrating the entire bar because we're trying to add up all the small increments of every bar to give us the electric field produced by the entire bar. So we're going to be going from 0 to L. So doing this integral is pretty simple. We can take all the constants out, and it just becomes a 1 over 50 minus x squared dx. It's just a simple u sub with u equals 50 minus x. Du is going to be negative dx, and our upper limit becomes 50 minus L, and our lower limit becomes just 50. So our integral becomes k lambda, our two constants, times the integral of 50 to 50 minus L of 1 over u squared du. And there's a negative that came with the negative du from right here. Okay, now we can go ahead and take the integral. So the integral of 1 over u squared is just negative 1 over u. So the negatives cancel out. So we get k lambda of 1 over u from 50 minus L to 50. Now we can go ahead and simplify this further to give us that it's going to be k lambda times 1 over 50 minus L minus 1 over 50. Okay, now we know that L is equal to 25 meters, and K is equal to a constant, which is 8.99 times 10 to the 9 newtons times meter squared over coulombs. But what is lambda? So if you go back up here, we saw that lambda is equal to Q over L. The total charge from this problem is, it's not shown, but believe me when I say the total charge is 25 coulombs. So we're going to be doing 25 coulombs over 25 meters, giving us 1 coulomb per meter. So every meter, there's 1 coulomb of charge for this rod. Okay, so now we know what lambda is. Lambda is 1 coulomb per meter. We can just simplify, and we can get that 9 times, or not 9, sorry, but 8.99 times 10 to the 9th newtons meter squared over coulomb squared times 1 coulomb per meter times, well, 50 minus L is just 1 over 25, and we can just put the units in now, meters, minus 1 over 50 meters is approximately, or if you round up, equal to 1.80 times 10 to the 9th newtons per coulomb. So that is the magnitude of the electric field produced by this charged rod of uniform charge. Now you can see that this answer is very close to the answer we got for the exercise in the video before this one right here. So what does this tell you? Well, this tells you that this charged rod behaves the same as a set of evenly spaced charges. So this set of evenly spaced, 25 of these evenly spaced charges act the same as a charge of normal distribution would behave, meaning that the electric field produced by both of them is the same, which is pretty cool. And that's pretty much it for this example. Thank you for watching, and see you.